And I'm Koji Okitani from Sheffield. I'm going to talk about pressure Hessian and dynamics of the Jacobian matrix. An introduction, it is important to study the velocity gradient in Euler, 3D Euler equations. And in this talk, we will denote by capital V to denote this gradient of velocity. And the dynamics of this guy is affected, as you know, the pressure Hessian. Of course, pressure is a non-local quantity, and this causes a serious problem. And the contents of my talk will be organized as follows. Since my talk is set after lunch, so I thought we need an eye-opener just to avoid snoring during my presentation. So I will start off by giving you a simple quiz. And I move on to explain the heart of the matter. And hopefully I will propose a model equation for the Jacobian matrix. This is the schedule. And first of all, the equations are now familiar with standard notations, 3D incompressible Euler equations that can be written like this. It's incompressible, and this capital D by dt is Lagrangian derivative. And if you use vorticity, you may write it, recast it like this, vorticity equation, standard stuff. And of course, we have the first integral, which is called, which may be phrased that the vortex lines are material. And one way to put it is just this capital Lagrangian derivative and directional derivative in the direction of vorticity commute. Okay, these are the standard stuff. And if you take a second Lagrangian derivative of vorticity, we may write the equation like this. And here, capital P is the Hessian matrix of pressure, which I did not define, but this is second spatial derivative of pressure. And you may derive this equation in a number of different ways. And I will show you one example how to derive this in the next slides. And the quiz is, can you spot what's happening therein? I mean, what's the underlying mechanism? Okay, here we go. So define this velocity gradient, capital V, by taking gradient of the Euler equations. This capital V satisfies the following evolution equation. Well-known thing. This is the definition. So all is fine up to here. And then all of a sudden, if we introduce an auxiliary variable, the matrix W, like this, then you can derive that equation. This is one possibly shortest proof of that guy. Have you ever seen this before? No? This is kind of undergraduate business. Because if you heard of this name, Italian mathematician, Riccati equation, Riccati substitution, and you may learn in your calculus course a scalar version of that equation. And there, then I will explain. This is kind of a simplest example of Riccati equation. This is ODE, ordinary differential equation. In this problem, we need to find a function of y, a function of y as a function of x, given the initial condition. There, we learn two things. The first one is perform the following transformation and introduce another variable u. Then this u solves second order equation with this forcing term in front. So I use the same capital P thing just to mimic or suggest the pressure Hessian. But if you do the similar thing for the vector equation, for this one, you can immediately get that equation. Of course, when you do this trick, recursive substitution, you implicitly introduce that material matrix W. Because if you multiply W from the right-hand side, you get dW by dt is VW, which means each column vector in this matrix is a material vector, right? So if you take, in particular, vorticity is a special case of material vector, and hence that equation follows. So this is a way of proving that equation. And this was written by some time ago in a paper by Craig. I'm not sure if he is the first one.
I'm sure he's not.
But this is not the main point. This is kind of one of introductory
but
business.
he's written or published, I don't know.
All right. But anyway, so this is the quiz. I hope you are now awake. And the point is, we learned two things about that equation. And another second property of that equation is, if we find one solution to that equation, we can generate all other solutions by simply solving linear equations. And this can be done as follows. You substitute like this. This is a known solution, one particular solution, and you write down the equation for u, and you get this form. And you further substitute introducing a new variable z, and you finally get it linearized. And this can be solved quite easily and explicitly like this. You don't have to see this in detail. Okay, and the rest of my talk will be, I'm concerned, will be application of these theories. We have already used property 1 for the Euler equations, but we have not used this second property. So the objective of this talk is to apply this to second property to the 3D Euler equations. Okay? But there is a catch to that. You may already know this. In this case of ordinary differential equations, this capital P of x is a given function of x, which has nothing to do with the initial data, this guy, y. So if P of x is given, you can choose arbitrarily the initial data and solve it arbitrarily. So you can get infinitely many possibilities for solutions. But in this case, this is pressure Hessian. Assume that this is given. But you cannot take initial data for v because velocity and pressure are related. So you cannot have huge freedom. Nevertheless, we can still play the game. Can you see why?
Depends what game. You're not going to reduce Euler to...
I mean, the game is, can we apply this second property to the 3D Euler equations? And actually, by accident, we have talked about the essence this morning. The reason is we are dealing with ideal fluids, which is conservative. That means if we have one solution, you will have another solution which is running backward in time. This solution is invariant under time reversal. So you may choose another solution, the time-reflected solution, which is running backward. So my objective is, by using this property 2, write down the relationship between a solution which is running forward in time with the connecting with the another solution which is running backward in time. This is one objective. And to do so, this is the heart of the matter. To be more specific, we consider the equation for Laplacian of P. Normally, we use this equation as follows. If you are given velocity field, the right-hand side is known, and you solve this Poisson equation to look for P, 1P, up to additive constant. That we normally do. But we take a look at different point of view. So we see this equation from this side. So if you are given pressure or pressure Hessian, this right-hand side is fixed. And assume that you have one solution, U. But you can always put minus sign here to get another solution for this problem. And starting from this solution, initial data, you have another solution. This is this. In the case of two-dimensional case, using string function, you have got this specific form of operator, which is called Monge-Ampere equation. And this, again, of course, invariant under psi into minus psi. In 3D case, you may also write down the same equation using vector potential, but unfortunately, this has no name. But we don't need deep knowledge on Monge-Ampere equation. The comment I have given you is enough to get by. So we start from this equation for the velocity gradient. And first, assume we have got one solution, particular solution V1, and you do this setting, and you get that equation. Notice that V1 and U are all matrices, so they don't commute. So we have to keep track of the order of multiplication. And now you set Z to the equal to U to the inverse, and you get this equation for Z. And this I is identity matrix. And this is an inhomogeneous equation. And to solve that equation, as usual, we consider a homogeneous counterpart to that equation, which goes like this. And luckily, theory of Riccati equations, I mean matrix-valued Riccati equations, has been developed a long time ago, 40s and 50s. And according to this theory, the solution has the following form. This T should be represented by the following combination, J1 times C and J2. C is a constant matrix, and J1 here is the solution of that equation. And J2 is a solution to that equation. J1 is, of course, the equation for the Jacobian matrix. Okay? And this has no name on it. And there is a reference, read Riccati differential equations. You may be surprised. This thickness of book, the whole part is devoted to Riccati equations. You may wonder why one person can write so many things regarding that equation. The reason is, of course, it talks about matrix-valued differential equations. And actually, this has a lot of applications in control theory, and very useful. And we make use of some result from there. And now, so we have solved this homogeneous equation in this form. Just to absorb this additional term is the same old trick called variation of constants. So here is a constant, but if we consider the time dependence on this guy, you can now solve the inhomogeneous term. And the solution for the z is given explicitly by this. Z is the solution to that guy. And if you take an inverse, you can get capital U, and hence you can get another solution, actually the other solution to the Euler equations. And explicitly, the other solution, capital V, is given by this. Okay? And as I mentioned, this the other solution should be the one starting from the same initial data but running backward in time. So it should be minus B1 at minus t. So if you plug this into here, you have a closed relationship like this. And here we have to assume that initial determinant of velocity gradient is non-zero because we have to take this inverse here. Under these assumptions, we have found an equation that governs, that relates a solution moving forward in time with a solution moving backward in time. So these two lines are the bottom line of my first part. So what? As I promised, I have applied recursive equation theory, this guy, to the Euler equations. And we have got one relationship, which is this. And to make use of this relationship, we will introduce an additional assumption. This is digression. I mean, just to explain the variation constants. And I think this is unnecessary, and I will skip this. This is undergraduate business. Yes, this is standard thing. I'll skip. And this part, to proceed, we will introduce one assumption, which is this. The time evolution for this velocity gradient is symmetric with respect to time. So suppose in a flow, if you find one particular fluid particle whose evolution is symmetrical with respect to time, then you can make further reductions. The reason is the following. To make progress, as I said, this J1 is simply identical to Jacobian matrix, but just J2 is similar, but the product is different in multiplication, and it has no name, and we have to solve it somehow. To handle this guy, let's note that the inverse matrix of the Jacobian matrix, let's say L, satisfies the following equation. If you take the inverse, you can reverse the order of product here, but with a minus sign. So under the assumption that this V1 thing is symmetrical with respect to time, then we can get J2 is actually an inverse of Jacobian at minus t. So now, from now on, we simply say J1, simply call J1 as J because it's Jacobian. Then J2 is given by J inverse at time minus t. So we can close everything in terms of J. with this assumption. And finally, you get the solution, equation for the Jacobian matrix, which is written like this. It's a nonlinear equation with a little bit of hysteresis in time. Actually, this is superficial, which couples the dynamics of J of t is coupled at Jacobian at minus t minus t. So to complete, we have to couple it with the dynamics of Jacobian at minus t. Then you can solve it. But as well known, as is known, eraser. We have a Cauchy first integral. One form of first integral is Cauchy, and this dx by dA is exactly equal to j. So of course, if j is smooth, nothing singular happens to j, omega is okay and no blow up. So if we have a blow up, this j should blow up. And assume, for example, a power law blow up for j, and we have to have dependence, 1 over time thing coming from this part. Because this is j, that's j, and this guy should be singular. And let's go the matrix inside this brace by capital A. Then you can easily check that determinant of A is constant in time. That means in order to have a singularity here, some elements of A must be singular. Okay? And this is a constant, and hence this integral part should become singular in finite time. Otherwise, no singularity is possible. So we will define a new variable here, j inverse at time minus t times jt. Let's call it phi. And you have got one closed equation for this matrix, which is written explicitly like that. And needless to mention, if it were not for this minus sign, j inverse j is simply equal to identity and trivial. But with this minus sign in here, it can behave in a non-trivial fashion. Okay, and the initial condition for this guy is identity. And if you assume the power law blow up like this, and you do the power counting, balancing both hand sides, and for the 3D case, you arrive at the conclusion that this n must be greater than or equal to 1. On the other hand, for the two-dimensional case, this n should be 0, and no blow up like this is possible. I think this is consistent with the global regularity of two-dimensional Euler equations.
Sorry?
Yes?
What about the assumption that the velocity satisfies some
the sole assumption is this, essentially this.
Okay. You're assuming that?
I assume this, and of course, determinant of the velocity gradient should be non-zero. That's an additional. The two assumptions, and you get here. And the difference between this and that is formed. If you recall how to form inverse matrix 3 by 3 or 2 by 2, you form cofactor matrices or minors. In 3D case, these guys are quadratic in terms of Jacobian, whereas in 2D case, this is linear in Jacobian, and that is the difference between these things. And by the way, the BKM or Konstantin's criterion for the minimum rates of blow-up says essentially that this Jacobian must diverge 1 over time, and its inverse 1 over square root of time, the minimum possible rates. Hence, this combination is a product. So these say that phi should blow up, say, like 1.5 or smaller, because there may be cancellation. In this sense, this estimate or this result is consistent with this. And as I said, this is local in space. It is important. This is the ordinary differential equation for one particular fluid particle. If you find a particle which has that property, then the whole dynamics is described by that equation. And yes?
Can you elaborate on that assumption?
Elaborate assumption?
Elaborate on that. Explain it.
For example, the simplest case is if you have a stagnation point, if you have where velocity vanishes, okay, in that case, Lagrangian derivative and the usual partial time derivative are the same thing. And sitting on that stagnation point, if you integrate Euler equations forward in time or backward in time, and if you get a similar velocity fields, then that's a candidate. I mean, that's the point we are considering. This is the one simplest case. But in general, you may allow non-zero velocity field, but this is hard to keep track of. But I can't elaborate any further. So actually, I will come back to this point later, but at present, I am not aware of any example which has this property together with non-zero determinant. So at this stage, this may be a model. That's the reason why I put question mark. Model is this. So this assumption may have empty initial data. For this case, this is just a model. But I will come back to this later. And here we have integral over time, but by simply taking transformation to these guys, you can write down a set of equations which is local in time and space like this. So this is a simple ordinary differential equations. F and G are 3 by 3 matrix, 9 elements. We have 2 determinant conditions, which means 16 degrees of freedom. So if that assumption is okay, for this particle, you can describe its dynamics simply using 16 degrees of freedom. It's a remarkable simplification. Okay. Now, by the way, in general, if you write down the Jacobian matrix and consider its time evolution by using, of course, dj by dt is vj. This is just velocity gradient. If you have j, you may generate vorticity. If you have vorticity, you may generate velocity field by Biot-Savart induction, and hence you can get an equation like this. And as we know, this is non-local in space, and you can easily write this down, but it's not very terribly useful in practice. On the other hand, the equations we have shown, like this one, is local in space and time and much, much simpler. And here is the one example of Taylor-Green vortex. This is done by Xu et al. Journal Scientific Computation. And this is a typical figure. I took this because it has color figures and revealing a little bit. And this is a famous shear layers forming in the flow. And actually, this point is stagnation point, where the thin vorticity layer is forming. That's one point. And I have checked by running Euler equations forward and backward that at this point, that assumption holds numerically. Great. However, you cannot apply this machinery to that flow. The reason is this Taylor-Green initial data starts from the velocity where the third component is identically 0, which means the velocity gradient is a singular matrix. You cannot get inverse matrix. So this machinery says nothing about that point. So this is not my machinery does not work for this guy.
Maybe in the symmetry plane there, you need only the 2D equations for the
2D?
gradient. Yeah.
What do you mean by 2D?
The 2D part of velocity gradient. That is.
Oh, that's your favorite business. Yes, I understand.
Yeah, maybe this equation we get the equation called there too, and you can study like that.
Yeah, your question is too deep for me to answer immediately, so I will come back to you later. And so I went for some more general initial condition. Taylor-Green, initially they proposed like this. And historically, similar type of flow was considered by Orr prior to Taylor-Green. But if you look for the stagnation point, unfortunately, the determinant is 0. And so under this class of flows, I could not find a suitable candidate. And so, but still, chances are that we may find non-trivial example for such flows. And so the main part of my talk is kind of over, but here is an appendix. In an effort to find a suitable point to be studied with this equation, I considered this matrix. The rest is totally useless academically, but very useful educationally. Because for this initial data, if you compute its determinant, you can find this nice formula. Okay? And actually, I'm in charge of undergraduate module in linear algebra. And if you go for 4-dimensional Taylor-Green vortex, you obtain this determinant. Okay, this is 3-dimension, and that's 4-dimension. And hence, you may speculate easily in n-dimensional Taylor-Green vortex, the determinant may be written like this. So this may be a good example for the coursework or the example problems. So our students may work perhaps 3x3 or 4x4, but certainly not n by n. If you ask them to prove the general case using mathematical induction on n, I would get a horrible student feedback at the end of the semester. So I would not do that. But this is terribly useful for my business. And here is a summary. We have applied the theory of matrix-valued Riccati equations to study velocity gradient, and we derive an exact relationship for the Jacobian matrix. And under the assumption that velocity gradient is symmetric with respect to time, and we have got a closed equation. And outlook is search for non-trivial initial data, and its numerics is underway. And this search for non-trivial initial data is quite important, but not yet done. But for the numerics, it is relatively simple to solve this set of equations. It's ordinary differential equations. And given this equation, you may solve that equation for arbitrary initial data, apart from the dynamics of fluids. But I tried a number of initial data for this set of solutions. But for the solutions I get, this is preliminary. All of them grow at most exponentially in time. And so far I found no solution that shall blow up in finite time. This is not fluid mechanics. I'm talking about the solution of this set of ordinary differential equations. So I should not speculate anything about this, but if I find some non-trivial initial data which suits our machinery, I'm guessing that guy will also show exponential growth at most. So my feeling is that the class of solutions or initial point which satisfy these assumptions is very limited in nature, and hence the growth is kind of quenched in the long term. I think I should stop over here.
Thank you. Questions? Peter.
Your closed system requires J minus D times J to be the identity. Can you track?
I don't assume.
Right?
This
So
is not
you-
identity.
Sorry, J minus D, J inverse to be identity. Right? So there is, right? Can you track the J minus D, J inverse minus identity through the calculation? So consider that as perhaps unknown, perhaps you will make some assumptions about the behavior of that through the calculation and still integrate with that extra matrix there hanging around.
So you're suggesting the following, you're recommending me to follow the evolution of this guy using direct numerical simulation?
No, I'm not that guy. I'm talking the guy that you assumed is to be identity. You assume that you have reversibility. The J, if I go minus in time, I get the same as forward, right? Therefore, if I would multiply by the inverse, I would get the identity. Therefore, I have an error that is 0 in your assumption. In general, it's not 0, but I suggest to put that in the equation and track it around.
Hence, we may find
In
where
general,
this,
what's the equation? In terms of this error term.
You are suggesting one possible method for searching
Right.
the suitable points for that sum. Oh, that's a good idea.
My question is, what about the initial conditions that you presented about a year ago in which Miguel has generalized? Are they in this special class?
That's a difficult question. In that case, we could reduce the whole dynamics basically onto two-dimensional
Right,
problem.
I know that, yeah.
And if you ask, this assumption, whether this assumption restricts ourselves to the essentially two-dimensional dynamics or not, I don't know.
James.
Quite early on, you had something about the relationship between the pressure and the velocity.
Yes.
So if you turn these things around, you can essentially you end up in 2D anyway with this. Here we go. So with the Monge-Ampere equation on the next slide.
Yeah.
for determining psi from P.
Yeah.
Do you know anything about the solutions of this equation?
This is well-known set of Rayleigh and uniqueness thing. At most, there are two solutions. That depends on the boundary condition, I think.
Sorry, for this equation, for the top equation.
The
Given a P.
maximum number of solutions for that guy is 2.
And
So we have found 2, and that's, I think, exhausts everything.
and where can I find that?
Curran-Hilbert, for example.
Okay.
Under no assumptions on P. Because it's kind of well known if the
Smooth. No, it's smooth.
you don't need positivity of the plus.
But the determinant is the non-vanishing of the determinant.
Curran-Hilbert, or there are specialized books like Gursa. You know Gursa? French guy is specialized in this business. Tons of works piled up.
Ian, did you have a question?
I was just going to say that there's a paper by Michel Larchevêque on exactly this paper with I'll show it to you.
Okay, well, let's thank our speaker again. And let's have a break for 15 minutes and reconvene at